Hi everyone and welcome to Big Face Robotics. In this video I'm going to get some motors spinning as part of my project to build a new mobile robot. I'm sharing the step-by-step process from ideas through design and testing to the finished robot. I started by giving the robot a face using a TFT screen and connecting up some sensors, but a mobile robot needs to be able to move around. So in this video I'll show you how I got the DC motors that I need for this project working and how you can do the same for your own robotics projects. I'm using a DRV8833 motor driver connected to an ESP32 to control the speed and direction of two DC motors. I'll take this one step further and connect AS5600 magnetic encoders to measure the motor rotation and implement closed loop motor speed control using a PID controller. So stay tuned. I am continuing work on my new steampunk inspired mobile robot project by connecting the various electronic components and testing their interface with the ESP32. I now have a disembodied robot nervous system on my workbench with each of the individual components tested and some testing done on the system as a whole. The goal by the end of this video is to show the motors working under closed loop speed control with a way to measure the number of motor rotations for distance measurement in the future. I will cover my selection of motor, how to use the DRV8833 motor driver, how I'm powering the motors, and how to connect and read encoder data from the AS5600 magnetic encoder modules. I will then explore the software required to control the speed and direction of the motors using a PID controller. At the end I will get everything working together, ready for the next step of the project. My robot will need a way to move around in the world, and the design I'm planning is a differential drive arrangement with two wheels driven by DC motors and a third idle wheel. I'm using these inexpensive TT gear motors for this project. They are readily available, cheap and low power, meaning the electronics required to drive them are also inexpensive and simple to use. I simply soldered wires to the motor terminals and connected the wire ends to a plug, ready for connection to the motor driver in the next step. To drive the motors, I'm using a DRV8833 motor driver, which is a very common module to pair with small DC motors. I have a few of these from previous projects, and the first job was to salvage a module and connect some wires and connectors, ready to hook the module up to the motors at an ESP32. To wire up the motor driver, I decided to solder wires directly to the module and fit plugs to these wires. This is part of the planned modular design of the robot that I will discuss in the future, and it means I don't need a custom circuit board to connect the module to. With the wires connected and plugs installed, I wrapped the module and capped on tape to prevent any damage or short circuits during testing. Here you can see the connections required by the driver module that I am using. There is a voltage supply to the module for powering the motors, and this also powers the driver itself, so no additional power supply is required, which is nice. The out pins are connected to the motors as shown. The in pins are connected to outputs from the ESP32 so that we can tell the motors when to run and in what direction. As I mentioned, if these pins are connected to pulse width modulation outputs, the motor speed can also be controlled. There is an enable jumper on the module that I am using, which needed to be soldered closed to enable the driver. Before I can get to spinning motors, I need to get power to the motor driver module and connect the motors themselves. For power, I will be using a 7.4 volt lithium ion battery to power the whole robot. I decided now is a good time to set up the battery, regulator and voltage monitoring that I will need for the project later on. I built a small circuit board for power distribution with the battery power connected to it via a small rocker switch. This circuit also includes a potential divider so that the battery voltage can be measured using an analog input on the ESP32. The resistor values I chose are shown here. with the aim of reducing the battery voltage to around 1 volt. The board serves to allow multiple connections to the battery voltage. One supply was connected to the motor driver and another to a regulator which will ultimately power the ESP32 and other electronics. This needs to be set to 5 volts as the regulator I am using has a variable output, and I will set it up now so that I don't forget. This can supply power to the ESP32 via connection to the 5 volt input pin. The last pieces of this particular puzzle are the AS5600 magnetic encoders. I already have these mounted to the gear motors from a previous project using some 3D printed brackets and magnet holders. These encoders sense the position of a rotating magnet to determine the position of the motor shaft. They use a diametrically magnetised magnet which needs to be mounted a few millimeters from the AS5600 chip on the PCB module. The bracket connecting the encoder to the gear motor is a design from a previous project that I will be reusing for this robot. The design is simply a bracket to hold the AS5600 in the correct place and a coupling piece to attach the magnet to the rotating shaft. The magnet is just press fit into the coupling piece, which is in turn press fit onto the secondary gearbox shaft, one of the handy features of the gear motors I'm using. I already had some wires connected to the motors and encoders, but I needed to extend them for this project. I have again elected to connect wires and plugs directly to the motors and the encoder modules, as you can see here. A bit of soldering and crimping was required, but the end result was 2 motor gearbox units with attached encoders and suitable length wires and connectors. The AS5600 modules require a 3.3 volt supply, a 0 volt connection, and I2C clock and data connections. I'll discuss more on how these are connected to the ESP32 when we get to testing. So here we have the final circuit all connected up, ready for testing. I'm using up the GPIO quite quickly in this project, but I have enough for now. I'm keeping track of what pins are assigned to what function for when the circuit is made more permanent. One of the benefits of prototyping the circuit on breadboard first is that changes can be made very easily, as there is often something that will need changing during testing. The next step is to install the required libraries and start writing some test software for driving the motors and reading from the encoders. So finally we can get some motors spinning. I'm using a library called ESP32 Servo to help with the pulse width modulation signals to the motor driver. I'll put a link to the library along with any others mentioned in the description below. Once the output pins being used are set up for pulse width modulation, a value can be written to the pin to drive it at the required duty cycle. A pulse width modulation value set lower than 255 will run the motor at a slower speed. Note that at a value less than about 150 the motor won't spin at all. This is because the voltage is too low to overcome the friction of the gearbox. This is where closed loop control will come in handy later. A quick test program was written to run both motors at varying speeds, changed using the touch input. The reference speed can be seen displayed on the TFT screen. The AS5600 encoders connect to the ESP32 via I2C and also require 3.3 volt and ground connections. Much like the VL53 LOX modules from my previous video, all of the AS5600 modules have the same I2C address. Unlike the other modules, there doesn't seem to be a solution to change the I2C address unless you choose the AS5600L variant, which doesn't seem to be anywhere near as common. The solution in this case is to put one encoder on the hardware I2C bus and the other on a software I2C bus, which is quite easy on the ESP32. For the encoders, I'm using a library called AS5600 by Rob Tillart. This makes it very easy to connect to the AS5600 modules and read from them via the I2C bus. One module is connected to the default I2C bus and the second encoder is connected to 2 spare pins which can be configured as a second I2C bus using the wire library. For a first test I'm reading the cumulative position, which is the total number of counts from the encoder. There are many examples of how to read speeds and positions included in the library examples which may come in handy later. I wrote a quick test program to read positions from the encoders and display the values on the TFT display. The motor shafts can be turned by hand to rotate the magnets, and you can see a counter representing the shaft position relative to where it started. This count will increase if the shaft is turned in one direction and decrease if rotated the opposite way. I also added the function to reset the counts when the touch input was triggered, just as a test. The finale of this video will be getting the motors turning under closed loop control, but before we do, I would like to ask that if you enjoy these videos and would like to support my channel, please consider subscribing and giving this video a like. It's only a click, but it really helps. Thank you very much. It's taken quite a few steps to get here, but with everything wired and tested, I can now get the closed loop control working for the motors. If you look at this clip, both motors are being sent the same voltage from the motor driver, but one is turning, the other is not. This is likely due to variations in the motors and gearboxes, friction, wear, etc. If these motors were trying to drive a robot forward slowly, the robot would be turning in circles. Closed loop control uses feedback from the encoders to make sure that each motor is turning at the required speed. To implement this, I will use a PID controller, helped with the use of this PID library. I'll add the details in the description. Once set up and tuned, this will monitor each motor speed versus a set point, work out the error and adjust the output to the motor to maintain the correct motor speed. I wrote the code for the PID controller and tested the result. It was hard to tell, but the controller was working, but the motor speeds were jumping all over the place. This was because the PID controller had not been tuned and so was very unstable. Some trial and error later, and I managed to find some gain settings that resulted in a controlled output to the motors. Here you can see the motors running under closed loop control. The speed is consistent and both motors are turning at the same speed. This is particularly noticeable at slower speeds. The reaction time of the controller is a bit slow at the moment, so the PID loops will require more tuning. But that will be a job for the future, as the tunings may change when additional gears, wheels and the weight of the robot itself are added. The PID controller can control the motors in both directions by simply setting a negative set point to reverse the direction. This means that the PID controller is now able to control the speed and directions of the motors. I tested slowing one of the motors down with my hand, and you can see the controller will attempt to adjust the output to the motor to maintain the required speed, showing that the controller is working as it should. So I have reached my goal for this video, to get all of the motor control components connected to the ESP32 and the software working enough to drive the motors, use the encoders to measure the gearbox output speed, and use a PID controller to implement closed loop speed control for the two motors I need for this robot. So the electronics are pretty much completed and tested enough to continue to the next stage of this project. Other than getting a servo working and an analog input to read the battery voltage, which are both fairly straightforward tasks to complete. So the next job will be to make a start on the first module for the robot, which is very exciting. In the next video, I want to start looking at the mechanical design of the robot and start working on the brain module. This will involve some 3D CAD design and 3D printing the first parts for the robot, so be sure to join me next time. So that's all for now. Thanks for watching, and hopefully this video has been useful, and I'll see you in the next video. Goodbye.